Hello everyone. In this video, we're going to talk about absolute convergence. By definition, we say that a series sum of an converges absolutely if the sum of the absolute values of the an's converge. We saw a bunch of examples of absolutely convergent series when we talked about alternating series. For instance, the sum from n equals 1 to infinity of minus 1 to the n plus 1 over n cubed is absolutely convergent since when we take the absolute value of every term, we get the sum from n equals 1 to infinity of 1 over n cubed, which is a convergent p-series. On the other hand, the sum from n equals 1 to infinity of minus 1 to the n over n is not absolutely convergent, since when we take absolute values, we get the harmonic series, which we know is divergent. However, notice that the original series converges. So, it's possible for a series to be convergent, but not absolutely convergent. We have a name for such series. These are called conditionally convergent series. So, we just established that there are series that are convergent, but not absolutely convergent. Is the opposite true? It turns out the answer is no. More precisely, if a series is absolutely convergent, then it is convergent. To see why this is true, notice that every an is bounded above by the absolute value of an, and bounded below by the negative absolute value of an. Taking sums, we find that the sum of the an's is bounded below by minus the sum of the absolute values, and bounded above by the positive sum of the absolute values. Since the series is absolutely convergent, we have that the big series and the small series both converge, and so this squeezes the middle series to converging as well. This argument is really just to help build some intuition, but the takeaway here is that we have a new way to tell that a series converges. That is, by proving that it's absolutely convergent. Let's see how this works in some examples. We saw earlier that the sum from n equals 1 to infinity of minus 1 to the n plus 1 over n cubed is absolutely convergent by the p-series test, and so it is convergent too. As a less trivial example, let's think about the sum from n equals 1 to infinity of sine of n over n to the fourth. We want to show that this series converges absolutely. So let's first take absolute values. Now, we notice that the absolute value of sine of n is bounded above by 1. So the sum of the absolute values is bounded above by the sum of 1 over n to the fourth, which is a convergent p-series. Therefore, by the comparison test, the sum of the absolute values converges. In other words, our original series is absolutely convergent, and thus converges regularly as well.